Homework from 5.1. The first one that I assigned was, as one of the ones that you had to do was 5D. And so here we had the matrix 1, negative 2, 0, 1. And with 2 by 2 matrix this is kind of quick, can be done quickly, right? And so the question was about find all the eigenvalues and then a basis for the eigenspaces. So the first step 1 is the characteristic equation. Just a nice name, that's why we keep saying it. And what we do is we take the same matrix but subtract lambda from the diagonal and then put that equal to 0. Here it's very quickly, we see that it is 1 minus lambda times 1 minus lambda. There's no off diagonal. That's equal to 0. There's only one solution, namely lambda equal to 1. If you remember from what I said in the lecture video, for upper triangular matrix, which this one is, the eigenvalues are just the diagonal elements, which confirms here our calculation. So that was step 1. As I said, very quick. Step 2, well, there's only one eigenvalue, so we will only have one eigenspace. So a basis for the eigenspace of lambda equals 1. Okay, so what we do, we replace, so we're going to replace this lambda here now, so we're going to put lambda equals 1 in here. Okay, so what we get the matrix 0, negative 2, 0, 0. Okay, now a base for the eigenspace, this means what? That we need to find the null space of this guy. Okay, don't remember what this means. So how do we do that? Well, so it actually is in row reduced form except for the 1 here. So we do this one single little guy to get a 1 where we want it. So we do this one and we get the echelon form 0, 0, 1. So this means, as always, we have a pivot here and therefore a free variable here. So x1 is a free variable, but x2 is a pivot variable. Okay, it doesn't happen much that x1 was the free variable, right? But in this kind of questions, it can quite often happen. Okay, so what does this mean now? We have to write down x1, x1, x2 in terms of x1. Okay, x1 is just itself. And what is x2? Well, x2 times 1 is 0, is equal to 0, right? So that's 0. So this is x1, 1, 0, and so this is our basis vector. Okay, and this means that this is a line, right? So the line that consists of all the multiples of 1, 0, each of these is an eigenvector with eigenvalue lambda equals 1. Now, I didn't assign this, but I think, let me quickly see here. Give me a sec. I think that I want to show this, that things can be different here. We will talk about it today in the lecture as well, but I want to do, I do want 5C. Sorry, I had to look for it. So this is an extra, right? This was not the thing I didn't want you. Well, you needed to do it, but I didn't ask you to do it, to hand it in. Okay, so so what is happening here? Just sorry, I want to get back to the actual question. That was the matrix 1, 0, 0, 1, which is of course ridiculously simple. We can actually see what the eigenvalues are because it's a diagonal matrix, in particular is a triangular matrix, and we have said it is just the element then on the diagonal. But you can as well very quickly do this, right? If you would write down the characteristic equation, that means you just subtract lambda from the diagonal elements, then this is just 1 minus lambda squared equal to 0. This means lambda is 1. But you could have right away say this is a diagonal or an upper triangular matrix. I'm just going to make it that, upper triangular matrix. And so we know that the eigenvalues are the diagonal elements, but there's only one. I mean, there are two of them, but they're both the same. So here's lambda equals 1. So that's as you on step 1. Now step 2. So this is a similar situation as before, right? We had a single eigenvalue. This can happen. And now what about the eigenspace? But you see something else what happens now. What is this matrix? So the matrix that we have to do now is you plug in this matrix, you plug in, why did it go, come on. You put in lambda equals 1 and plug this in this matrix, but you get 0, 0, 0, 0, the 0 matrix. Now that is row reduced echelon form. You have to, it's a bit weird, but let's just think about it. What are the pivot variables? Well, a pivot variable is a variable that has a 1. The column where there's a 1. There is no column. So there are no pivot variables. That's weird, right? But it can happen. This means both x1 and x2 are free. Okay? So let's write this out. What is x1? Well, x1 is x1, right? We have x1 and x2. Well, x1 is just x1 and x2 is x2. We said each time we have a free variable, it's just equal to itself. Okay, and then we have to write this as x1, 1, 0 plus x2, 0, 1. Right? We separate the part with the x1, the part with the x2, and then this is a basis, which is actually the standard basis. So the eigenspace, if you think about it, this is the basis of the whole space. Therefore, the eigenspace is everything. Is that surprising? No, this is the identity matrix. And what is an eigenvector? An eigenvector, so this is A, right? And if you do A times U, if this is the identity matrix, you get U. And this means that the eigenvalue is exactly 1 here, right? There's nothing there, so but that means there's a 1. So every vector is an eigenvector. That's what this means. But what I also wanted to point out is that notice that here the basis was a single basis element. Here we have 2 basis elements. So we cannot predict the dimension of this null space, of this eigenspace. I just want to point that out. Okay, so let's do number 11, the other one that I had assigned. Now this is going to be a little bit tougher because we're going to have to deal with 3 by 3s, and those have always give us more difficult equations to solve. Okay, so this is the matrix A. So step 1, the characteristic equation. And that in itself is 2 parts, right? So first we have to find the equation, then we have to solve it. So actually I should perhaps split it into step 1, 1 and step 1, 2 or something like that. So let's start with this equation itself. That means we take the matrix, just copy it. That's why I prefer my way than the book's way, where they turn it around. And then you subtract minus lambda of the diagonal, only of the diagonal piece, nowhere else, only the diagonal elements. And now we have to calculate this and put this equal to 0. When it comes to determinants, especially if it's more than a 2 by 2, we're going to have to do some trickery of our determinants. It's a little bit more tricky here because we're dealing with things that have a variable lambda. Lambda is a variable here, right? So it's a bit trickier than just working with regular matrices, determinants. But I see a good thing. I don't know whether you guys see this, so let me put this. We know that we have to put it equal to 0, but let me just get rid of this, okay? I'm going to expand here with using this column. I could also have the row, column 2, because there's all zeros there, so we only have. So remember, if you expand along a row or a column, only do this really if you have everything is 0 except for one element, and then that one element comes out, 3 minus lambda, and then we are left with the cofactor. Now we have to also always think about the sign. That is a plus, a minus, a plus. Diagonal elements are a plus. So we actually have a plus sign here. Now, since we are dealing with the equation that we want to put equal to 0, it doesn't matter this much. So you can make a mistake here, but try not to, of course. So we have 4 minus lambda minus 1, 1, 2 minus lambda. So that would be 3 minus lambda. And we have then 4 minus lambda times 2 minus lambda minus 1 plus 1. Now, don't expand this, right? We need a factor. We're going to have to put this equal to 0. So I have already a factor. So they were very nice that this This time it was not hard to find the factorization, but in general it could be tricky, even for third degree. And so now we have, but this one we have to expand. Why? Because this is not factored, right? There's a plus here. This plus means it's not factored, so I have to expand here. So FOIL this out. That is an 8 minus 4 lambda minus 2 lambda plus lambda square plus 1. So I get 3 minus lambda, and then I have, let's see, let's write it in descending order, 2 lambda square minus 6 lambda plus 9. 2 elements that multiply to 9 add up to -6. I see that is lambda minus 3 and lambda minus 3. And so we put this equal to 0. So what is the solution now here? What are the solutions? Well, each of these factors can be 0, and if you put a 0, or you put this 0, or you put this 0, what you get? Each time the same answer, lambda is 3. So here's another case, even we have bigger matrix, and still it has only one eigenvalue. Okay? So this can happen. In general, of course, if you have a 3 by 3, in most general case, it will actually have 3 eigenvalues. And a 4 by 4 will have 4, because you get the degree 4 equation. But sometimes these eigenvalues so-called coincide, as we say. Okay, so that's step 1. Step 2, the eigenspace. So the eigenspace, or a basis at least, but I'm a bit lazy, right? So 4 lambda is 3. So what do? We take our matrix that we had and we replace lambda by 3. So let me write this here. I'm doing lambda equals 3, and I'm going to plug this in. Okay, keep it here. 4 minus lambda, that is 3, 0, -1, 0, lambda is 3, okay, that's 0, great, 0, 1, 0, 3 minus, 2 minus 3 is -1, okay. Did I do this right? Yeah? Right. Why am I doubting myself? I don't know why I'm doubting myself. I think I did it right? Okay. Oh. No. I didn't. I knew there was something wrong. Lambda, I put this, lambda is 3. See, sorry, it's because I just moved away that I didn't see it. Lambda is 3, so this becomes, of course, 1. Yeah. Okay, good. We have to row reduce this, which is rather quick, because we have already a 0 row. That's very good news. And then row 3 minus row 1. And that is also going to give me a 0 row, right? I hope you see this, because they're the same. So we get 1, 0, -1, 0, 0, 0, 0, 0, 0. So, okay, our analysis now. This is the echelon form, but it's actually a reduced echelon form, right? Because there's only one row. Everything above this pivot has to be 0, but there is nothing above it. So, yes. So this is reduced echelon form. So we are done. Okay, so the blue one is the pivot variable, that's x1. And therefore, the other two are free variables, x2, x3. Okay, and now we write them. We unite. Let me keep the colors a little bit, that you see a little bit what the difference is here. So x2, x3. Okay, so x1, that's a pivot variable that has to be written in terms of the green variables. So that is x1 plus 0, x2 minus x3 equals 0. So that means x3 here. Okay. X2 is a free variable, so it's equal to itself, and so is x3. Okay, so we see, we split now the part that has an x2 in it, that's 0, 1, 0, and then the part that has an x3 in it is 1, 0, 1. So this is a basis for our eigenspace. And notice here that we have two vectors, two basis vectors, so this eigenspace is two-dimensional. But we're sitting inside the three-dimensional space, right? Okay, that's how these questions go, and I won't do anything else anymore. That's all that I assigned for now. And then, by the way, if you ever have any problems with other homework problems, you can always let me know, right? You can email me, or so I can, I can either answer you quickly if it's possible to do it over email, or I can make this extra video if I notice that this might be of general interest. Okay, don't stop communicating with me. I mean, I know you have to already do so much with quizzes and homeworks and so, but feel free to ask things, right? Or in the comments, you can ask things in the comments as well. No, I'll see all these things. Don't worry about it.